This conference will now be recorded.
Hello everyone, we'll start with problem, but there will be topics after problem discussion, and those are liquid state and different properties of liquid state, that is vapor pressure, surface tension and viscosity. Fine. So what is critical temperature, pressure and volume, that we have seen in the last class, which is based on Andrews experimental observations. Okay. So A and B, these two are basically Van der Waals constant. And here from this we have to understand that which gas will be more easily liquefiable. So the question is saying that A and B, these two are Van der Waals constant, that you already know. But from these two values, how it is related to the fact that how easily it can be liquefied. That is the relationship between how easily the gas can be liquefied and the A and B, these two constant, that relationship we have to understand. But here it is already mentioned the fact that chlorine is more easily liquefied than the other gas, ethane. So ethane is C2H6 and chlorine is diatomic halogen, Cl2. Now, as it is already mentioned that chlorine is more easily liquefiable compared to ethane. From this we have to choose the correct option related to A and B. So option A, it is saying that A and B for chlorine is greater than, that is both A and B for chlorine is greater compared to the other gas. Then it is less. Then option C is saying that A is only greater but B is greater for C2H6, and in case of D it is the reverse statement. Now which one of this will be correct, that we have to understand. Now what is the relationship with A and B? Now A means what? A means when we see that the value of A is very high, that means intermolecular interaction is very high. And the value B, that is actually the measure of the volume which is occupied by the particles of gas only. Fine. So when A is large, as A is measure of magnitude of the attractive forces between the molecules of the gas. That means when A value is high, the gas particles, their intermolecular interaction between them, that will be very high. That means you can easily bring them close to each other, which means that liquefaction will be very easy. So when A is very high, liquefaction will be easier process. Now what about B? The B is basically the effective volume which is occupied by the gas particles, and the value of B is related to effective size of gas molecules also. So basically, as it is the total volume of all the gas particles, so obviously it is directly connected to the effective size of gas molecule, because that volume is not available for the movement of the gas particles, right? So that is the reason when gases are having very high B value, that means compared to the total volume of container, suppose the volume occupied by all the gas particles, I am not trying to say that all the gas particles they are accumulated in at a particular corner. No, I am not trying to say that. I am just saying, suppose if you being close to each other, that means this is the total volume compared to the volume available in the space. So volume available, suppose it is V, and these particles together, the volume is small v. That means this amount of volume that is not available for the movement of these particles. Only this zone is available, but not the zone which is basically the total volume of all the gas particles, B. So B value high means what? That their movement will be gradually, that is, this space will be very low. So ultimately what relation we can see, that gases with higher value of A and lower value of B, that they will be more liquefiable. So that is the reason if we see that A for chlorine, that is actually greater than A for ethane, because only then it is possible that you can do the liquefaction very easily, because it is already mentioned that it is more easily liquefiable than ethane. And when space availability is very less, that means when B value for chlorine it is very high. That means what? This available volume is very less. Now available volume less means what? You can easily bring them close to each other. Sorry, it will be high. It is not lower. Actually, when A is high, then also liquefaction will be easier. When B is high, then also liquefaction will be easier. Because when B is high, the space availability is now less, and when space availability is less, that means the molecules, they cannot move very freely, and when they are not able to move freely, obviously liquefaction of these gas particles, that will be easier. So that is the reason this option is the correct option. A for chlorine greater than C2H6, B for chlorine is greater than C2H6. Next question. Consider the van der Waals constant A and B and for the following gases. So there are how many gases present? Here we have argon, neon, krypton and xenon. Now which gas is having highest critical temperature? That we have to find. These two values are given for these four gases. Now Tc, that is highest critical temperature is denoted by Tc. And Tc, what is the relationship of Tc with small a and small b? That I have shown in the last class. So it is basically 8a by 27 Rb. Now this part is basically constant, isn't it? 8 by 27 and R is the universal gas constant. So without the constant, now you can write that Tc is directly proportional to the ratio of A by B. So when A value will increase, obviously Tc will also increase, and when B value will increase, Tc will decrease. So we have to check the ratio for all these four gases. So here the ratio will be max. When the ratio will be max? When A is very high, B is very low. So highest ratio of A by B, that will lead to max value of Tc. So if you do it for argon, it is basically 1.3 divided by 3.2. So this is for argon. Then if you do it for neon, it is 0.2 divided by 1.7. Now this is less than 1. So this is also basically less than 1. Then for krypton, now it is very high. 5.1 divided by 1.0, which is almost equal to 5. And for xenon, it is 4.1 divided by 5. So maximum ratio we are finding for krypton. So that is why Tc will be maximum, that is highest for krypton gas among these four options. So this is the correct answer. Yeah, that is option 1. Fine. So now we will move to our actual discussion, that is liquid state. So this chapter, that is states of matter, here basically two states, that is among liquid and gaseous. Mainly it is this chapter is all about gaseous state, and there is some information related to liquid state, and solid state is basically not present in this chapter, which is in 12, class 12. Another unit is there. Fine. So after finishing gaseous state, now we will see liquid state. So in a liquid state of matter, obviously they are now less tightly packed if you compare with respect to solid, because in solid the distance between particles is almost nil. But compared to solid, obviously now it is less tightly packed. But if you compare with gas, now it is more tightly packed. So compared to solid, less tightly packed, compared to gas, more tightly packed. Force of attraction between particles is weaker compared to solids. So that obviously has to be true. But if you compare with respect to gas, then force of attraction between particles stronger. Now, unlike gases, where we have seen that we can do liquefaction by compression process. But if you want to do the same compression for liquids, obviously they are not compressible like gases, because the distance between the particles, it is already very, very less compared to gases. Then how we will do compression? That is not possible. So here particles already have less space between them to move. So further compression is not possible. So when suppose you have gas and you are decreasing, you are increasing the pressure, there will be very huge effect on the volume. But if you do the same pressure change for liquid, now the difference between the initial volume and final volume, it is not so marked compared to the situation that you see in case of gases, because they are not so compressible. In case of liquids, there is fixed volume but not fixed shape. So that is why you can keep liquid in any shape of container, whether it is glass or bowl, whatever. But what is the difference with gas? In case of gas, there is no fixed volume also. No fixed shape, no fixed volume. But when it is liquid, only the volume is now fixed, but shape is not fixed. And when you move to solid, now both are fixed. So these are the differences. So they can take the shape of container in which we are keeping them. So these are the different features of liquid. Molecules of liquid can move past one another freely. So that is why we can say that they can flow just like gas. So this is one property which is common for both gas as well as liquid. Okay, so that is the reason both are called fluid. Because anything which can flow, you can call them fluid. So solid, in case of solid, that is not possible, so it is not fluid. But liquids can do so, can flow. It is also possible for gases, so that is why both you can call fluid. Together you can call it fluid. Here some important properties we will focus for liquids, and those are vapor pressure of liquid, surface tension of liquid, and viscosity of liquid. One by one we will discuss all these three. So what is the difference between gas and vapor? That I mentioned again, that is already. But if you want to do the same explanation in terms of critical temperature, because critical temperature in the last class we have seen what it means. It is that temperature above which you cannot do liquefaction. Whatever is the value of pressure, it doesn't matter. So when a gas it is below critical temperature, that means you can do liquefaction when you are applying pressure. And under that condition, you can call them vapor. So remember, in Andrews experiment, there is a dome-shaped zone, and the peak, that is this type of dome curve we have seen. So gradually, when we increase the temperature, this flat region decreases, and ultimately one region will reach when there is no such flat region. So this is the peak point, and there is this type of dome shape. So only when the gas is present inside any point of this dome shape, then only liquefaction is possible. But this is basically TC. So once the gas is crossing the value of TC, even if you increase pressure, you will not be able to liquefy. Okay. So when in terms of critical pressure, what is the difference between gas and vapor? Gas is below critical temperature. When it can be liquefied, then it is called vapor. But once it is crossing the value of TC, liquefaction you cannot do, and then you have to call it only gas. Or in other sense, without critical temperature, in general, if you say what is the difference, gas is something which is under normal condition in gaseous state. But vapor is, we call the gaseous state of water as vapor, because water under normal condition is not liquid. You heat, you provide heat, then it is converted to gaseous state, and then you can call them vapor. But under normal condition, it is not gaseous. So that is why we cannot say it is gas. We have to call it vapor of water. Or from bromine liquid or from iodine solid, there is some vapor we can observe under, that is liquid. It is violet color vapor for iodine, or for bromine it is orangish type of color for the vapor. So in that case you can call vapor. But for hydrogen or carbon dioxide, nitrogen, all these substances, they are under normal condition gas, so you have to call them gas. So these three properties we will discuss. So here we have that is the initial idea. That is what, as a definition, what we can say. So vapor pressure is the pressure exerted by the vapor of a liquid or solid. So mainly here we will focus on liquid, not solid, because sometimes there is also conversion possible directly from solid to gaseous state. But we are not focusing on that. Here it is simply mentioned because it is definition. But Just focus on liquid. It is the pressure exerted by the vapor of a liquid on the liquid when it is thermodynamic equilibrium at a given temperature in a closed system. Okay, so remember, there should be constant temperature and there should be a closed system also. That is energy transfer, that is not possible. So if we can maintain that is thermodynamic equilibrium, that is we will discuss this obviously in detail. So here we have just initial idea what is vapor pressure. Vapor we know what it is, that we have mentioned here, but what is vapor pressure, that definition is given here. So it is a vapor, it is a pressure exerted by the vapor of a liquid on the liquid, that is from which it is generated. Pressure will be applied on that. So suppose we have some liquid and from the surface of the liquid there is some vapor. So it will generate the pressure on the liquid. So that is, it is written of a liquid on the liquid when it is thermodynamic equilibrium condition at a given temperature in a closed system. What about surface tension? Surface tension is the property of the surface of a liquid, and it is a tendency of the liquid to reduce the surface area as minimum as possible. And viscosity, it is basically applicable for both liquid and gas, because viscosity is something which is property of fluid. It is the resistance property of fluid, and fluid means both gas and liquid, but here mainly we will focus on viscosity of liquid, not for gas. But in general, as a definition, you can say it is the resistance of a fluid, liquid or gas, to its motion. And why the resistance is generated is because of internal friction between the layers of fluid. So one by one we will see in detail all these three features. So first we have vapor pressure. Here we have this graph. You can see vapor pressure unit is atmosphere is taken in y-axis, temperature in degrees Celsius taken in x-axis. So when temperature is increasing, vapor pressure is also increasing. Molecules of a liquid, they are having a tendency to escape from the surface. So here suppose we have any container, you have taken some liquid and there will be a tendency from its surface. So this is the surface, to form vapor above the surface through evaporation process, that is conversion from liquid state to gaseous state. When a liquid is placed in a closed container, the liquid undergoes evaporation, and after evaporation the vapors that are generated, suppose here some vapor generated, now this vapor can again condense and it will be converted to liquid again. So both processes are possible. So gradually what will happen, there will be equilibrium. So when equilibrium is reached, because the process, that is the container is closed, so it is not open, so that is why the rate of evaporation, that is there is evaporation process going on, condensation process going on, but when the rate of these two processes are equal, there will be equilibrium. Fine, both the rate are now same, that is first liquid is converted to vapor and then vapor is converted to liquid again. So the first process is evaporation E and this process is condensation C. So this pressure which is exerted by the vapor when it is in equilibrium with the liquid, remember when it is in equilibrium condition, not just at any condition, then it is known as saturated vapor pressure, or sometimes it is called simply vapor pressure. Now there is a particular temperature at which vapor pressure of liquid that can be equal to the external pressure. Now until now we have said that it is closed container, but suppose if it is not closed, now what will happen, one point will be reached when the external pressure of the environment and the vapor pressure of this liquid, these two will be equal. So when this situation will reach, then there will be, that is at this temperature, now what will happen, it will be directly converted to the vapor. So it is no longer again condensed and condensation going on, again it is converted liquid. No, now it is not that, because it has already reached the external pressure. So that is why this temperature is boiling point where boiling will start. So now from liquid state it will be gradually converted to the gaseous state. Fine. Now boiling point, when you mention, basically you have to also mention the pressure. Now, and that is normally what we consider, that is the external pressure. Environment, we consider it at 1 atm, or rarely sometimes 1 bar also. But remember, 1 atm, 1 bar are actually close to each other, but it is slightly less, because that is, which one is less? Bar is slightly low, that is from unit wise. If you consider, 1 bar is equal to 0.986 atmosphere. So atmosphere is slightly greater than bar. So that is the reason, if you mention boiling point at 1 atmosphere pressure, then it is called normal boiling point. If you consider it at 1 bar, though these two values are very close, because you can see these two are very close, it will not differ much. So now it is called standard boiling point. It is the difference. And obviously, as 1 bar is slightly lesser than atm, because 1 bar is equal to 0.986 atm. So atm is greater. So when pressure is high, then standard boiling point, obviously pressure high means what? To convert from liquid to vapor, now more temperature will be required, right? That is, boiling point will be increased. So that is why standard boiling point, which is basically at 1 bar, and normal boiling point, which is at 1 atm. So it is obviously standard boiling point, it will be slightly lower, because when you are saying 1 atm, obviously this is greater than 1 bar, because 1 bar is equal to 0.986. So when it is 1 atm, obviously now this is also increased. So as atm is slightly higher unit, so standard boiling point, which is you are measuring at 1 bar, it will be slightly lesser compared to normal boiling point, but more or less it is almost same. So with increase in pressure, obviously boiling point is also increased. Fine. So here you can see some substances are given along with their vapor pressure, and also it is mentioned at which temperature, because if you do not mention vapor, when you are mentioning the vapor pressure value, if you are not mentioning the temperature, it will not be correct, because with increase in temperature there is also increase in vapor pressure, which you can see from this graph, right? So obviously constant temperature you have to check the vapor pressure. So here it is at 25 degrees centigrade, and look at this, ethyl ether, then we have bromine, ethyl alcohol, water. So maximum vapor pressure you are seeing in what case? You are seeing in this case. Then gradually it is becoming less and less. So basically among these 4 substances, the values of vapor pressure you can see, and you can easily correlate it with their boiling point. So diethyl ether, it is basically very low boiling point, around 34 degrees centigrade. Then ethyl alcohol, it is around 78. Water is 100 degrees centigrade. So as you are moving down, basically boiling point is increasing, and it is directly related to this vapor pressure. So at same temperature, if you have 2 substances, one substance is having more vapor pressure, that means what? This conversion from, that is evaporation, is occurring, and liquid is converted to vapor. That means it can easily convert from liquid to vapor. It easily go from liquid to vapor. Why it is possible? Because, and that is related to some other reason, because of intermolecular interaction, that you will see. But important point is, when vapor pressure is high, for that is, you have 2 substances, one substance vapor pressure high, that means you can easily convert them to gaseous state. And easily convert to gaseous state means what? Boiling point is low. So when vapor pressure is very high, boiling point will be low, which is clear from this 4 examples. Though boiling point is not mentioned, but as you move down, boiling point is basically increasing. Ethyl alcohol 78, water 100 degrees centigrade. Fine. So now we will see what are the factors from which you will be able to understand that it will have higher vapor pressure, and accordingly you can also decide whether it will have higher boiling point or not. So first point we have here, type of molecules. Now type of molecules, basically it is what type of intermolecular forces are present. Remember, in this chapter, in the first class, we have discussed intermolecular forces, that is van der Waals forces. So there we have seen dipole-dipole interaction, then London dispersion forces, hydrogen bonding, everything it is under van der Waals forces. So when these forces are very strong, obviously vapor pressure will be low, because when it is in liquid state, it is liquid state, it is vapor state. Now the particles, if that is the intermolecular forces between two particles, if it is very strong, obviously you cannot convert them to vapor state so easily, because now this interaction is so strong, and when they are moving from liquid to vapor, basically the distance between them is increased, but that is not so easy because of the strong intermolecular forces. So when this force is very strong, vapor pressure we cannot expect very high, so it will be low. But when it is weak, vapor pressure will be relatively high. Now remember, in the last example, ether and water. In water, hydrogen bonding is present, which is strong. But in ether, there is no such thing. So obviously, ether is having that is relatively weak intermolecular forces. So vapor pressure high and boiling point is low. Here we have these two examples. One is ethyl alcohol, another one is diethyl ether. I have just given the example of diethyl ether and water. You can also consider ethanol. So diethyl ether is basically this structure. In short, in general, how we can write ether? When both sides are symmetrical, it is alkyl group, then oxygen, then alkyl. So here we have ethyl group both sides, so that is why we are calling it diethyl ether. Forces present are basically weak dipole-dipole force, because oxygen carbon bond is present. So oxygen is more electronegative, so you can expect some polarity in this bond, that is dipole will be generated. But it is not very strong, weak dipole-dipole forces. And London dispersion forces, this is basically the weakest force, but it is present in any molecule. So on the basis of it, you cannot decide whether it is, that is, as a whole, the molecule will be having more strong intermolecular force or not. So you just have to focus on the other force, because this is present in any molecule, whether it is polar or non-polar. What about ethyl alcohol? Now in case of alcohol, basically it is formula ROH. Now both sides you do not have alkyl group, one side you have H, and this bond, that is OH bond, which is not present in the previous case. In the previous case you have carbon oxygen carbon bond. Now the polarity difference between O and C and the polarity difference between O and H, obviously it is high. So now the dipole-dipole force, London dispersion, it will always be present, as I have said. And hydrogen bonding is also a type of dipole-dipole force, but it is a special kind of dipole-dipole force. So, and it is that is here also dipole force present, in ether also dipole force present, but in case of ethyl alcohol, this special type of dipole-dipole force, which is hydrogen bond, is very strong. So obviously that is between two ethyl alcohol molecule, the force that is present, and between two diethyl molecule, the force that is present, in the previous case it is stronger. So you cannot that is bring them far from each other. It is difficult. So that is the reason for ethyl alcohol, vapor pressure will be low and boiling point will be high. So this is ethyl alcohol, vapor pressure low. This is diethyl ether, vapor pressure high. Next point is temperature. So first is what type of intermolecular forces present. If you want to know what are the factors affecting vapor pressure. Second thing is temperature. So in the previous slide you have seen the plot, vapor pressure versus temperature, right? See this plot I'm talking about. So at high temperature, more molecules are now having enough energy to escape the liquid surface and they are moving to the gaseous surface. But when it is compared to lower temperature, so suppose you have taken any particular substance, suppose you have taken ethyl alcohol, don't take two substances because in that case it means you have changed the substance. So now basically we are trying to see the effect of temperature. So you have to just have one substance and you have to check the vapor pressure of this substance at two different temperatures. Suppose you have taken ethyl alcohol, you are checking the vapor pressure as 25 degrees centigrade, which is already given here 0.08. And you are also checking ethyl alcohol's vapor pressure at some other temperature, suppose at 80 degrees. So obviously now it is high. So for same substance, when you are increasing temperature, now they are the molecules, whether it is ethyl alcohol or any other substance, the general, that is common point is now the molecules will be having more energy compared to the lower temperature and they can easily escape the liquid state and they can move to vapor state. Fine. But when lower temperature, fewer molecules now have sufficient energy to escape from the liquid state or solid, though mainly we are focusing on liquid. So that is the reason when temperature of a liquid increases, vapor pressure also increases, directly proportional. Okay. So after vapor pressure, next is surface tension. So as the name suggests, surface tension. So in the surface of liquid, there will be some tension. But what is so special about surface? Why not bulk? Look at this container. Suppose you have any molecule here and you also have another molecule inside. So which is molecule in the bulk? So when you have taken it, now there is balanced force because force will be exerting equally. Or you can, in the reverse way, you can say that the other particles, they are exerting the same force. So it is spherically, that is three-dimensionally, if you imagine, it is same from all the sides. That is one side, it will be nullified from the opposite direction. But if it is at the surface, now that is sphere, if you consider, imagine a sphere, in the, unlike the previous case, now basically that is not possible. Only lower half, there is half type of sphere you can imagine, right? So molecule when it is present at the surface, because some molecules will be present at the surface, some will be in the bulk. So the molecules that are present at the surface, now the force is not balanced because here you do not have any liquid, you only have it in the lower part. Okay, so now the force is not balanced. So the particles in the bulk of liquid are uniformly attracted in all directions, net force acting on these molecules zero. But the molecules that are present in the surface area, now what will happen? They will experience net attractive force towards the interior of the liquid. So they will feel a pressure inside compared to this area. Okay. So the forces acting on the molecules on the surface, it is not balanced. So that is the difference if you have any molecule at the surface or if you have it in the bulk. Hence, liquids have a tendency to minimize their surface area. So as there is a inner pool always going on, so they will try to minimize their surface area because any substance, they always try to become more stable. I mean, as stable as possible. So when there is some pull lower from the lower side, if there is some pull, so there will be a tendency to minimize the surface area as much as possible. So as if they are under tension, and the surface will act as if it is a stretched membrane, because from one lower part there is a pull and it is not that is balanced, it is imbalanced force is present. Surface tension, how it changes with temperature? It basically decreases as the temperature is raised, because when temperature you are increasing, it has effect on intermolecular attraction. Now intermolecular attraction decreases, and when the attraction between two molecules decreases, that means this pull from the lower part, that is not so high. So that is the reason surface tension is now decreased as temperature is increased. Now, definition of surface tension, it can be given in both ways. So sometimes you will see in books it is mentioned surface tension. So when you are using the term surface tension, now the definition, look at the unit also. Surface tension unit is Newton per meter. So it is basically force acting per unit length. Force unit is Newton in SI, and per unit length meter, Newton per meter. So if you want to give the definition of surface tension, it will be force acting per unit length, which is perpendicular to the line drawn on the surface. So on the surface, if you draw a line like this, suppose these are the unit length, this is one unit length, this is another unit length. So per unit length, the force that is present acting per unit length perpendicular to the line drawn on the surface. So this line I have drawn on the surface, and suppose this is a unit length and there is an inner pull occurring. So per unit length, the force that is acting, that is surface tension. Unit is Newton per meter. But if you want to say in terms of energy, that is also fine. You can also say that the energy required to increase the surface area of liquid by 1 unit. Now why we are saying so? Why energy will be required? Because there is an inner pull. The surface area, it is trying, the liquid will be trying to minimize the surface area as much as possible. So if you want to increase surface area, obviously now you have to provide energy. By 1 unit, suppose you are trying to increase the surface area, you have to provide energy. So how much energy you will provide per unit area? Now area is basically meter square if you consider SI. So per meter square, what is the energy required? In joule, energy unit. So joule per meter square. Now that is in terms of surface energy. If you say, this is another way of saying that is the same definition, but now it is surface energy. It is not surface tension, but both are actually meaning the same thing. Whether you give the definition in terms of surface tension or you give the definition in terms of energy, it doesn't matter. Okay. Here we can see some surface tension. Look at the unit. It is millijoule per meter square. So basically, if you say simply joule, the value that you are seeing here, 18, it will be 0.018. But if you say in terms of millijoule, then 0.018, you are just multiplying 3. So now you will get a figure which is easy to handle. There is no decimal. So that is why it is in millijoule per meter square. Because values, if you directly express in joule per meter square or Newton per meter, it is with this type of figure, 0.0 something, okay, 0.018, 0.023, 0.024. So that is why here we have taken millijoule per meter square or millinewton per meter, whatever you say. Fine. So here we have these substances, solar liquid, N-hexane, then ethanol, acetone, ethylene glycol, and we have water. So see, surface tension values are given. Maximum value it is for water. The last property we will see is viscosity. So viscosity is also possible for gas, but here we are focusing only for liquid because we are discussing all about all the properties of liquid, not gaseous. So it is a measure of resistance to flow which is arising because of internal friction between layers of a fluid. So here in this picture, suppose we have a tube like this. Suppose just imagine 3-dimensional tube, and in this tube you can imagine, suppose this is the outer surface, inner surface, suppose there is another tube. Actually there is no tube, you just have to imagine, if you consider this is another layer of liquid, then inside is there is another layer of liquid. So 3-dimensional, if you cut one, that is this tube, there will be area. So this is the area, right? But if you simply consider in 2-dimensionally, then this is one wall of the tube, this is another lower wall. So here these are the different layers of the liquid. Now this layer, which is most, that is just inner, here the velocity is maximum. Okay, so see the velocity is v. But when there is unit distance difference, now it is decreasing by dV, very small amount. So we have to just imagine as if there is different layers of liquid. Similarly, when you are moving down from this most middle layer, if you see, this is the most middle. When you are moving down, then also there is decrease. So similarly, when you again move lower part, it will again decrease. So in this way, when you will move to the wall, here it will be almost zero. So it means as you are moving from the wall, gradually when you are moving towards the middle zone, the velocity is basically the velocity of the liquid layers, it is increasing. That means when you are moving towards the wall, surface of the wall of the tube, there is some resistance occurring. So this is actually because of viscosity. It is a measure of resistance to flow. There is some resistance towards proper flow. Maximum flow is possible in the middle zone, so that is why V is max. But as you are moving towards wall, because of this resistance, because of this viscosity, there is gradually resistance increasing as you are moving towards the wall because of internal friction and also because of the layers of a fluid. So they slip past one another during flow. Fine. So it is a measure of resistance to flow arising because of internal friction between layers of a fluid as they slip past one another during flowing. Fine. So when it is flowing through a tube, the central layer has the highest velocity, that is V. Now, as you move towards wall, the layer along the inner wall in the tube remains almost stationary, as if zero. So here friction is maximum. So because of this situation, that is different part of this tube, you are getting different velocity. Basically, you are getting maximum in the central zone, but there is a velocity gradient exists, and velocity gradient exists in the laminar flow. Now see, for fluid, when you consider flow, whether it is liquid or gas, just consider liquid here. When two types of flow possible, one flow is very smooth flow of liquid, that is actually laminar flow. Another flow may be turbulent type of flow. There is some turbulent nature. So we are not talking about that because when it is moving through the tube, obviously it is laminar flow, smooth flow. So you have to consider that laminar flow. Velocity gradient exists across the cross section of the tube. So this is the cross section you can see. Now how we measure this viscosity, that is measured in terms of this eta sign. So here on these terms, what it means, F is basically force, that is equal to minus, it is called eta. Then we have area, then we have dV dz. So this is the viscous force F on a layer of area A. You just consider any layer. There is some particular area located at a place having velocity gradient dV dz. So dz is basically distance between two layers. So suppose this distance is dz. So here you can also take this distance as dz. Basically all are dz. Now this is the most central part. Here velocity is max. So if you just move to the next layer, now it is v minus dv. So v minus dv means what? If you take the difference between these two velocity, obviously it is v minus dv minus v. So vv cancelled, it is dv, that is the difference. So this dv dz, that is speed difference divided by the distance between the two layers. This is known as velocity gradient. How much velocity is changed with respect to the distance dz, that is velocity gradient. So velocity gradient, then area, and this is basically eta, and that is equal to force. Now if you bring all these quantities in the left hand side, you can get the unit of this eta. Okay, so viscosity is expressed, it is all actually this letter is eta, but what we call it is coefficient of viscosity. the SI unit of eta is Newton second per meter square. So Newton second per meter square, this is one unit you can use. And another unit that you can use is Pascal into second, because Newton into meter square, that is actually pressure Pascal. How much force you are applying per unit, that is per area, because meter square is area. Meter per minus 2 means per area how much force is there, and also it is multiplied by second. But second as it is, if you simply consider n into m minus 2, that is power minus 2, it is Pascal. So any of this unit we can use, fine. But in CGS system, it has another unit which is basically 1 gram per centimeter per second, which is also called poise. Now you can see that if it is in CGS, obviously in SI it will be 1 kg per meter per second. Just meter is centimeter is now meter and gram is now kg. Now how you can do it from this Newton second per meter square? So Newton is basically 1 kg, that is not, I will not write 1, it is in place of Newton you can write it is kg into meter per second square, and there is already a second present, right? That means ultimately what you are getting? You are getting kg into, sorry, there is meter square also. So this meter square and meter, ultimately you are getting per meter, second minus 2 and second you are getting per second. So see what you are getting, same unit, kg per meter per second. So this part is basically n, then there is s, then there is m minus 2. So I have just put all the units individually. So if you break the Newton unit, you will get kg into meter per second square, per second, and second it will be per second square, and second it will be per second, and m minus 2 and m, that means it will be m minus 1. So ultimately you are reaching the same unit, and Pascal, that is actually equal to n meter square. So in this way you can also, if you bring all this unit in the left hand side, because force unit, that will be Newton, then area which is basically meter square, but this side it will be meter per square, then dz, that is basically distance, it is meter, so here when you will bring it in this side it will be meter, and dv is basically meter per second. So ultimately what you are getting in meter square, let me do it clearly. So n, that is, it is basically f into dz divided by a into dv. So in place of f, if I write Newton, then if we write dz, which is basically distance, so it will be meter. Then in place of a, if I write meter square, and in place of dv, which is speed, it is meter per second. So meter if it is cancelled, so ultimately what you are getting, Newton per meter square into second. So see, it is same which is mentioned here, that is the SI unit of it. So in this way we can understand what is the unit of this poise, eta. But when you use CGS, then it is 1 poise, because it is difficult to write this large unit, so simply you can write poise. Factors affecting viscosity, intermolecular attractive force, they affect viscosity. So when there is strong intermolecular attractive forces present, obviously it is difficult for the molecules to move with respect to each other. Now the resistance will be very high. For example, if you take ethanol, the formula is CH3CH2OH. But when, suppose if you are replacing one of these H with another OH, now the formula is changing to HOCH2CH2OH. So CH2, CH2, 2OH. So in ethanol there is 1OH, now there are 2OH. Obviously viscosity will increase. So look at the value, it is eta Pascal into second. This is the value, but when it is ethylene glycol, how it is increased. So that is the proof that intermolecular attractive forces, when it is strong, viscosity will increase. Next is shape of molecules. Liquids consist of long flexible molecules. Suppose the molecules, their shape is such, it is very long hydrocarbon chain or something like this. It will have higher viscosities, because higher viscosity compared to what type of shape? Compared to those which are more spherical in shape or shorter chain. So when there is this type of long flexible chain, then there will be high viscosity. Because when the molecules are very long, suppose you have long hydrocarbon chain, it is easier for them to be tangled with one another. So the chain can tangle with each other. So it will be more difficult. Now the resistance will be high. So that is the reason, if you look at the values in the table, bitumen, which is having very large structure, its value is so high, 10 to the power 8. Fine. And obviously temperature, viscosity of liquids, inverse relation with temperature. So when temperature is increased, the viscosity of liquid decrease. But remember, though we are not discussing it for gas, but for gas, there is increase in viscosity with temperature. Then the relationship is different. But here it is decrease with an increase in temperature. Okay. So only for liquids it is inverse relationship, not for gas. So this part is complete. As we have some time, so we can discuss one problem which is based on, that is overall, that is, if you consider this chapter states of matter, we can discuss one or two problems. So here the problem is saying that initially the root mean square velocity, which is root over 3 RT by capital M. M is molar mass of nitrogen molecule at a certain temperature given small u. Suppose you are now increasing the temperature to double amount, and as a result all the nitrogen molecules dissociate into nitrogen atom. So initially it is nitrogen molecule, but now you are getting individual nitrogen atom. So here the molar mass is 28, 14 plus 14, but here the molar mass is 14. So molar mass not same. So it is asking now, when you are increasing the temperature to double value, what will be the effect on RMS velocity? So if we consider the initial value, it is basically root over 3 RT divided by 28. But if it is the final u, which is suppose u prime, now it is 3R into 2T, because you have increased temperature. And instead of writing 28, now we will write 14. Now take the ratio of these two. What you will get? I will keep all the quantities inside this root. So it is 6 RT now. So it is 2 RT cancelled. So it is 2. This is 3, 2. So we are getting, sorry, it will be, let me write it clearly. I have written a wrong ratio. So u prime you have to write fast. So it is 6 RT divided by 14 multiplied by 28 by 3 RT. RT cancelled. This is 2, 3, 6, 2. So ultimately you are getting root 4, which is 2. That means the new RMS velocity is double of the value of the initial. So the new value is 2u. So the new RMS is option 1 should be the correct option. So here the informations are mentioned. I have already shown the calculation. New temperature 2T and new RMS, suppose it is u prime, and the new molar mass will be 14, because now you have to consider nitrogen atom. So first option is the correct option. One more problem. The volume of a gas is twice, gas A is twice than that of gas B. That means if I consider VB, then VA is basically 2VB. Okay. Then compressibility factor of gas A, that means ZA, that is thrice that of B. So it is 3ZB. So these are the information given. You have to find the pressure of the gases of equal number of moles. So what is the relationship between the pressure of these two gas? Pa for A gas, Pb for B gas. Now the relationship between, that is, remember ideal gas equation is PV equal to nRT. But here if you also consider Z, what we know, what is the ratio? It is basically PV nRT relationship. So from this what you can write? Z is equal to PV by nRT. So P should be equal to Z into nRT by V. Now here this N is constant because it is mentioned equal number of moles. So for both gas it is same. R is constant, temperature is same. Okay. So if that is the case, now we can write that pressure is directly related to the ratio of Z by V. So for the ratio of PA by PB, it will be ZA by ZB into VB by VA. Now if you put the value of ZA, in place of ZA you can write 3ZB divided by, already there is Z. In place of VA, now you can write 2VB. So VB cancelled, these two cancel. You are getting 3 by 2. That means 2PA is equal to 3PB, and it is matching with which option? First option. Okay. So in this way, we can find the pressure of the new gas. Okay. Because number of moles and temperature both are same. So we are at the end of the session. Thank you for listening.